Hi everybody, this video will cover section 1 of chapter 4 entitled Inverse Functions. However, before we talk about inverse functions, we are going to chat about one-to-one functions. And what is a one-to-one function? Well, this function on the left here is a one-to-one function. Notice that for every single value of x, this function will produce for you a different value of y. Even in this interval where it's difficult to see, every different value of x will produce for you a different value of y. As a consequence, one of the things that you'll notice about this particular function is that this function is always decreasing. If I got rid of this minus sign, then this function would be always increasing, and that is a property of a one-to-one function. It is typically always decreasing, or it is always increasing. It can never be 0 because if it is, then you'll have different values of y, x with the same values of y, and if it becomes increasing at some point, then once again that function is going to cross different values of y or the same value of y for different values of x. As a consequence, this function here is not one-to-one. Notice that when y is equal to -2, or even when y is equal to 2, there are 3 values of x which will produce for you a y of 2. As a consequence, this function is not one-to-one. Also notice that this function decreases on certain intervals and then it increases on certain intervals. So basically, any function of even degree, x to the 4th, x squared, would not be one-to-one. Any function that is symmetric about the x-axis, such as this, this one is not. Any function that is symmetric about the x-axis would also not be one-to-one as well. So what can we say about one-to-one functions? Well, basically, if a function is one-to-one, then each x value corresponds to only one y value, and similarly, each y value corresponds to only one x value, which is why these types of functions are important when we are considering inverses. Now, the specific definition for a one-to-one function is this. A function f is a one-to-one function if for all elements a and b in the domain of f, if the following implication is true. If a is not equal to b, then that implies that f of a is not equal to f of b. Now, typically, when we try to show that a function is one-to-one, we tend to evaluate that function against this definition. And if it passes, it is, and if it doesn't, well, then it doesn't pass. If it passes, then it is one-to-one, and if it doesn't pass, well, then it's not one-to-one. However, this definition is very, very difficult to prove, however, there is an alternate way to prove it. And before I mention that, I guess I should show this down here. Different values of the domain correspond to different values of the range, which is basically just a less mathy way of saying this. Now, as I mentioned before, using this definition to show that a function is one-to-one is a difficult endeavor. However, there is another way to describe this implication, which is actually what this is, and that is something called the contrapositive. It is a technique that is used in many proofs. Basically, the way it works is that if this implication is difficult to prove, then the contrapositive can actually prove the exact same implication. And what is the contrapositive in this particular case? It is that if f of a being equal to f of b implies that a is equal to b for all a and b in the domain of f, then the function is one-to-one. Okay? And believe it or not, this tends to be easier to prove, and we will actually show that through an example. Now, how do you show that a function is not one-to-one? All you got to do is find a counterexample. Just find one example, 2 values of x, such that f of a is equal to f of b, then the function is not one-to-one. So this right here, if it's not one-to-one, is very easy to prove. If it is one-to-one, it's slightly more difficult to prove, but not necessarily as bad as one might think. And that brings us to these 2 examples. We want to determine whether or not these 2 functions are one-to-one. Well, I suspect that this one is one-to-one, so I'm going to see if I can go ahead and prove that. Okay, so I'm going to let f of a be equal to f of b. Well, what the heck does that mean? Well, that means that negative 3a cubed plus 7 is going to be equal to negative 3b cubed plus 7. This is f of a, this is f of b. Well, notice what are some things that we can do? Well, we have a plus 7 here, a plus 7 there. They will, if we simplify, these will cancel. And that leaves me with negative 3a cubed is equal to negative 3b cubed. I can divide both sides by negative 3, and then I have a cubed is equal to b cubed. And then I can raise everything to the 1/3 power. And since I'm raising everything to a rational exponent where the denominator is even, I don't need to worry about plus or minuses. And as a consequence, a cubed to the third root of a cubed is just a, and the third root of b cubed is just b. Now, what if we had the case where f of x was actually equal to, say, x to the 4th power? All right. Well, then we would have f of a being equal to f of b, which would imply that a to the 4th is equal to b to the 4th. Then we would take the 4th root. Now, if you remember from our discussion on in chapter 1 on equations with rational exponents, if I take something to the a rational power where the denominator is even, I have to consider both the negative and the positive values of one of them. I have to consider the negative and the positive values of the right-hand side. As a consequence, a can be either to plus or minus b, which essentially tells us which violates our condition of over here of f of a being equal to f of b implies a is equal to b, because here we now have that a is equal to b. Here we now have that a is equal to b and a is equal to minus b. So in this particular case, this would not be 1-to-1. Okay, now let's take a look at this one down here. This is f of x is equal to 49, the square root of 49 minus x squared. Now, if you were to plot that, it would look something like this. It will look at it like a semicircle, which starts at -7 and ends at -7. Okay, so you can look at this and you can tell that that's not 1-to-1, but how can you actually show that mathematically, not just graphically? Well, here we're going to use a counter example. Suppose we let's use a trivial case. Let's let x be equal to 1, or let me do it right this way. Let's let a be equal to 1 and b be equal to -1. All right, well, in that case, f of a, or f of 1, is going to be the square root of 49 minus 1, or 49 minus 1 squared, which is 1, which is the square root of 48. F of b, which is f of -1, is going to be equal to the square root of 49 minus -1 squared, which is just 1, 49 minus 1, which will also be the square root of 48. So here we found two values in the domain that produce the exact same value in the range. As a consequence, this is not 1-to-1. So this approach right here for determining whether or not a function is 1-to-1 is a little more difficult, but really isn't all that bad. Of course, the best way to determine whether a function is 1-to-1 is basically look at the graph. And once again, if the graph shows that different values of x produce the same value of y, then it's not 1-to-1. And of course, that also corresponds to what's called the horizontal line test. So just like functions had a vertical line test to determine whether or not it's a function or not, 1-to-1 functions have a horizontal line test. And of course, the horizontal line test is that every horizontal line must intersect the graph at most once. This one intersects the graph 3 times here. Of course, it only intersects the graph once here, which is great. But however, since it intersects the graph 3 times here, it's not 1-to-1. And of course, you really don't need to do a horizontal line test. You can actually just look at you can just look at the graph, and you can tell. which of course brings us to our next set of examples. Here we want to determine whether the graph of this function is the graph of a one-to-one function. Well, clearly this is the graph of a one-to-one function. This right here is y is equal to x cubed. So even though it looks like it's hitting a horizontal line, will hit a number of functions here, it really isn't. And you don't need to do a horizontal line test. You can look at this and you can tell that this is a one-to-one function. On the other hand, this one, which is negative x squared plus 4, is not a one-to-one function. Once again, you can just look at it and you can tell, right? You can tell just by looking, well, at this horizontal line, which we call the x-axis. You can clearly tell that this one is not one-to-one. And finally, this function here, which is a version of negative x to the fifth plus some constant times x to the third plus 1, is also not a one-to-one function. You can use the horizontal line test, but just look at it and you can tell. There's two values. There are two values of x which produce the same y here. Well, actually, there's three values of x, and same thing here as well. So you can use horizontal line tests. They encourage you to do so, but sometimes this is one of those cases where you can just look at the graph and then you know. Okay, what can we say about one-to-one functions? Well, we mentioned it before. One-to-one functions are either always decreasing or they are always increasing. And if you have a function that is either always increasing or decreasing, I think I forgot to underline that, along the entire domain, then it is a one-to-one function. Okay, and this pretty much is a summary on how to determine whether a function is one-to-one. Once again, if we show that f of a is equal to f of b implies that a is equal to b for all values of a and b in the domain, the function is one-to-one. If you want to show that a function is not one-to-one, all you need to do is find a counterexample. Find two values of x that will produce for you the same y value. Of course, if you have a graph, you can use the horizontal line test. You don't really need to explicitly do that. You can just look at the graph and it's pretty obvious. And then once again, if a function is always either increasing or decreasing on the entire domain, then it is one-to-one. If it is increasing in some interval or increasing in another interval, then that curve is going to turn back on itself and you'll have two different values of x that will produce the same value y and therefore not be one-to-one. Okay, so what is so great about one-to-one functions? Well, they're nice, well-behaved functions, and they also have an inverse function. And better yet, that inverse function happens to be one-to-one. Sometimes you call that inverse function f to the negative 1. That does not mean 1 over f. That basically means it's going to be the inverse. And sometimes we call it g. gy, I don't know. And if f and g are inverses, it works like this. If you take a value x and you apply you apply the function f to it, you're going to get a number. If you take that number and apply the function g to it, you will get x back. That's just another way of saying that the composition of g and f, when applied to x, will always give you x. And it will also work in the other way. Now keep in mind, remember that in general, the composition of g and f and g are not always commutative. But in this case, when you're dealing with an inverse or when you're dealing with one-to-one functions, they are. So the strict definition for an inverse function is this. F be a one-to-one function. Then g is an inverse function of f if, once again, the composition of f and g of x gives you x for every x in the domain of g, because we're starting with g. And also the same is true, the composition of g and f will give you x for every x in the domain of f. Remember, when you're written like this, we're applying f first. So the domain, the domain of this composition is going to be the domain of f, and then the output is going to be in the range of g, which, by the way, happens to be equal to the domain of f. Now, what if you did not have what if you tried to get an inverse for a function that is not one-to-one? Well, it turns out that functions that are not one-to-one also have inverses, but those inverses will not be functions. And that is the problem, because we want to restrict ourselves to functions. And also, I forgot to mention this, the inverse function, g or f negative 1, will also be 1-to-1. So it tends to go both ways, as we are kind of implying here. G is if G is the inverse of F, then F is the inverse of G. If F minus 1, F negative 1 is the inverse of F, then F is the inverse of F negative 1. Okay, the domain and range. The domain of F will always be the range of its inverse. The range of F will always be the domain of its inverse, which is a necessary condition for this relationship to hold. And that brings us to this example, deciding whether or two functions are inverses. Okay, well, so we're going to let f of g be defined by these two functions. Both of them are linear. And we want to determine whether or not g is the inverse of f. So how do we do that? Well, once again, we're just going to go ahead and apply our definition. Basically, we're going to look at the composition of f and g as applied to x. And if it turns out that's equal to x, then we're halfway there. Then we're going to look at the composition of g and f applied to x. And if that's equal to x, then we're good to go. Okay, so let's first look at f, the composition of f and g. That is going to be equal to f of g of x, which g of x is going to be 1/2 x minus 5/2. All right, so applying the definition of f, we're going to replace everywhere we see an x, so we're going to replace x with this argument, and that is going to give us 2 times everything that's in here. 1/2 x minus 5/2 plus 5. Okay, do the math. The 2 and the 1/2 cancels. We just have x. The 2 and the half over here cancels. That gives me minus 5 plus 5. And of course, that will be equal to x. So this works. Now we need to look at the composition of g and f. Okay, well, that is going to be equal to g evaluated at 2x plus 5. All right, once again, we are going to substitute 2x plus 5 everywhere we see an x in the definition of g. That will give me 1/2 times the quantity, 2x plus 5, minus 5. And then when I evaluate that, using the distributive property here, I have 1/2 times 2x, which is x. Oh, I'm sorry, this should be 1/2 times. Oh, this should be a 5/2. My apologies. I need to do the definition correctly. Then 1/2 plus 5 is going to be 5/2 minus 5/2. And of course, these cancel, and we have x. So this indeed is a 1-to-1 function. Okay. How do we go about finding the inverse of a 1-to-1 function? Now keep in mind that the composition of f with its inverse will always produce for you x. Okay? So we actually want to find those values which when we apply the inverse, I guess I should do that, will give us the exact same value. And notice that this is basically our x value, our y value, our x value, and our y value, and so forth. So it turns out that the inverse is basically nothing more than these ordered pairs reversed. So f of -1 is actually going to be the set 1, -2, 0, -1, 0. Oh, I'm sorry, that's 1, 1, 0, 2, 1, 3, 2. Does that work? Well, let's find out. Let's compute f inverse, the composition of f inverse of f evaluated at, say, 2. All right. Well, that's going to be f inverse evaluated at f of 2. Well, f of 2 is 3. Okay, and that will give us f inverse of 3, which will once in turn give us 2. So basically, to find the inverse of an ordered pair, all you gotta do is just switch the order of the ordered pair, and you're good to go. Okay, next we want to talk about finding the equation of an inverse. And how do we do that? Well, there's actually a nice handy-dandy 4-step procedure that you can use. I guess I got to find another phrase other than handy-dandy, I think. The first one is, well, you take f of x and replace it with y if it's necessary. Clearly your function, basically what that's saying is, well, your function is already equal to y, is y equal to ax cubed plus whatever, or whatever the function is. Well, then you don't need to do this, it's already done for you. Secondly, you want to replace your x and your y. All right. So if you did actually have something like y is equal to ax cubed, you want to replace the x and the y. So then you're going to have x is equal to ay cubed. All right. Then you want to solve for y. Okay. So in this particular case, we are going to have y is equal to x over a, all raised to the 1/3 power. And then I'm going to replace y with f negative 1 of x. And that's it. So in this particular case, if f of x is equal to a times x cubed, then its inverse is going to be x over a raised to the 1/3 power. Okay, how does this work? Well, let's take a look at these 3 problems. Here we have f of x is, here we want to determine whether or not each equation defines it should be a 1-to-1 function, not a function. And if so, find the equation of its inverse. Now this one is the absolute f of x is equal to the absolute value of x. Now notice that when f is equal to 1, or f of 1 is equal to 1, and f of negative 1 is equal to 1. This is not 1-to-1. Does not have a inverse that is a function. So we can skip this one and move on. Now for this one, this function is indeed 1-to-1. Trust me, it is. Okay, so now we want to find its inverse. Once again, what we're going to do is we're going to replace h of x with y. That will give me y is equal to x cubed plus 5. Now I want to swap my x and my y, and that will give me x is equal to y cubed plus 5, and now I want to solve for y. And that will give me that y cubed is equal to x minus 5, and then y is equal to the cubed root of x minus 5. And then I'm going to replace my y with f of x, and that will give me, now f negative 1 of x, that'll be f negative 1 of x is equal to x minus 5, that quantity raised to the 1/3 power. Okay, so that one's done. Now here we have a rational sucker. Is this 1-to-1? I certainly hope that it is. Actually it is. I'll leave you to prove that. What I want to do is show how we can actually turn this, find its inverse. Okay, so once again we are going to replace g of x with y. That will give me y is equal to negative 3x plus 1 divided by x minus 5. And of course this is not defined when x is equal to 5. Now I'm going to replace my x's and swap out my x's and y's. That's going to give me that x is equal to negative 3y plus 1 times y minus 5. Now I want to solve for y. So I can get rid of my denominator. That will give me xy minus 5x is equal to negative 3y plus 1. So now I want to get all my y terms on one side and all my x terms on the other side. And if I do, I will have xy plus 3y, adding 3y to both sides, and that will be equal to 5x plus 1. Now I can factor out my y. That would give me y is equal to x plus 3, which will be equal to 5x plus 1. And now I can isolate y, and if I do, I will have y is equal to 5 x plus 1, I don't know why I had the grouping symbol there, divided by x plus 3. Okay, now I can go ahead and substitute g to the negative 1 power, or no, not g to the negative 1, which once again is not 1 over g, it's just the inverse of g. And that will be equal to 5x plus 1 divided by x plus 3. And the domain of g will be all values of x except x equal to negative 3. It will exclude x is equal to negative 3. And that's pretty much all there is to it. Okay, graphing the inverse. Suppose that we actually have a graph of f. How do we graph the inverse? Well, it turns out that the inverse of the graph of the inverse is symmetric to f along the line y equals negative x. Now, what the heck does that look like? Well, basically, if this particular point, AB, lies on the graph of f, then the point BA, kind of like what we did when we found the inverse for those for that set of ordered pairs, will lie on the graph of f negative 1, or f inverse. Okay, so what does that look like? Well, here we go. Take a look at this. Here we have a graph of f. Basically, and this right here is really nothing more than f of x is equal to 1/3 x plus 1. What does the inverse look like? Well, here, notice I have 3 critical points. 3, 2, 0, 1, and then 3, 0. So if 3, 2 is on the graph of f, then 2, 3 is on its inverse. 2, 3, and it is right there. If 0, 1 is on the graph of f, then 1, 0 is on its inverse, right there. And similarly, if negative 3, 0 is on the graph, then 0, negative 3, almost messed that one up, is on its inverse, right there. Now, hopefully you guys have better artistic skills than mine. I think it's time to change colors. But then once you have those points, you can go ahead and connect the dots. I will do my best not to mess this up. And it will look, well, so much for my straight line, something like that. And if I actually drew it correctly, you can actually see that it is indeed symmetric about this particular line, which is x equals to y. Okay, so once again, it is pretty straightforward, particularly if you have straight lines. Just basically switch the order of your ordered pairs, plot them, or find critical points on your function. Find the ordered pairs for those points, switch the orders for those points, plot the new points, and then connect the dots. Okay, so this is all I have. This is all I have left to say about inverses. If f is 1 to 1, then then its inverse happens to exist, and it also is 1 to 1. The domain of f is going to be the range of f of f inverse, and the range of f inverse will be the domain. The range of f will be the domain of f inverse. If the point AB lies on the graph of f, then the point BA lies on its inverse. And once again, the graph of a function and its one-to-one function and its inverse are reflections across each other, or reflections of each other across the lines y equals x. And also this applies for functions that are not one-to-one. The graph of a function that is not one-to-one and its inverse was actually, once again, nothing more than a reflection, or nothing more than symmetric reflections are symmetric about this line. And if you show, and once you visualize that graph, you will see that the graph of the inverse would not be a function. And then finally, to find the equation for the inverse, just replace f of x with y, swap x and y, solve for y, and you are done. And this is all that I have for this particular lecture. Yes, it is. If you have any questions, please feel free to contact me. This is Bob Boyle, signing off.